Okay, the first way to measure test cases that we are discussing today is test coverage. Okay, so we already have some concepts about test coverage, and we already have some experience of like obtaining test coverage from test cases and reporting test coverage, right? So I here I give a simple example, right? I so about how to know how good a test set is. I The example is so testing an ice cream stand, right? So you want to you go to an ice cream store, you want to buy an ice cream, and you need to give your stand to hold this ice cream, right? So how can we test this ice cream stand, right? Test set one. So we test 3 chocolate cones, right? 3 chocolate cones. We put those 3 chocolate cones inside the ice cream stand. And the second test case in the test set one is to put a vanilla cone in the ice cream stand, right? We test chocolate and vanilla cones in a stand. Okay. In test set two, we put 1 chocolate cone in the stand, 1 vanilla cone in the stand, and 1 mint cone in the stand. We test 3 types of ice cream cones, right? The questions: do test cases cover full, partial, or little input space, right? So which test case is better? The questions, right? Or do test cases cover full, partial, or little implementation or the source code? 2 criteria. The first one is do test cases cover the input space, right? Second is do test cases cover implementation or the source code? So input space is we can input a chocolate cone or a vanilla cone or a mint cone as input space, right? Source code, a coverage of the source code is how much code we covered using our test cases. Okay. So to measure this test coverage, we can measure the coverage of input space and measure the coverage of the source code or measure the coverage of the implementation. So measurement provide a quantitative assessment of the effectiveness of our test cases or the quality or the coverage of our test cases. Okay. Um, so what is a definition of test case coverage? Sorry. So test case coverage is basically defined this way. So giving a set of test requirements, TR test requirements, giving a set of test requirements for a coverage criterion, C. A test set T satisfied C if and only if for every test requirement TR belongs to TR, at least one test set, one test case satisfies TR. Um, satisfies the so it looks complicated. The basic idea is if there's a coverage criterion C, and within C there are a set of test requirements. If we want to design a test set that satisfy the criterion C, so we need to make sure that for each test requirement we have one test case to satisfy it. Right? That is about coverage. Okay, the different coverage levels. Right. So we will talk about input and code coverage later. But basically, so given a set of test requirements TR and a test set, the coverage level is a ratio of the number of test requirements satisfied by T to the size of TR. I give a concrete example here. If our test requirements TR is we need to test different flavors, including chocolate, vanilla, and mint flavors. We need to test all three flavors. This is a test requirements, right? In our test set 1, right? So we have two tests, remember. In our test set 1, we test 3 chocolate cones, right? 1 vanilla cone. Basically, we test two types of two flavors, right? Then our coverage is just 2 divided by 3, which is 66.7%. Okay, it's a coverage level. So here we learned TR. What is TR, right? So TR is a test requirement. And a set of test requirements is included in a coverage criteria, right? And a test set is a set of test cases. So coverage level is what is the percentage of the test requirements that are tested in our test cases. Okay. So remember, sometimes there are infeasible test requirements that we cannot satisfy, right? For example, here in this code, right, you see we can never reach the statement within the if branch, right? Because if the condition is giving a false variable, so we cannot reach unreachable call within this if branch. So just remember, sometimes we have infeasible test requirements that we can never satisfy. Okay. So we talk about two input. We talk about two coverage types, right? Then we will talk about these two types of coverage, so one by one. The first one is covering input space. The second is covering code, right? So this coverage metrics would quantify the coverage of test cases, right? Like 80% coverage or like full coverage. It serves a purpose to derive the design of test cases. When we derive our test case, we have a goal, right? We need to meet 80% coverage. So when we design our test cases, we keep that goal in mind. Okay. First, let's talk about how to cover input space, right? Specifically, so we use an input space modeling approach. Okay. So in this input space modeling approach, so usually it is suitable for black box testing, right? Because we test input space, right? We don't care about the internal mechanisms of the code. In black box testing, we don't need knowledge of the implementation, right? So testing is based on input domains, right? So input domain to a program contains all the possible inputs to that program. This is the input domain. And input parameters defines the scope of the input domain, right? Like input parameters can be the parameters to a method in the function, in a code. It also can be the data read from a file or user level inputs, right? This is the parameters. So testing is fundamentally about choosing finite sets of values from the input domain. We have an infinite input domain. So we want to choose a finite set of values from this input domain. How can we choose test cases? Remember, we talk about partition testing, equivalence partition testing, right? So partition the input space into smaller partitions or classes. Okay. So this partitioning approach makes the idea more formal, right? So we just test one input from each partition, one representative input from each partition. But actually, we also test the border values, right? Remember, So here we consider if we test one representative value from one partition to simplify this discussion, okay? So input space partitioning is used for black box testing technique we just discussed. So there are two desired properties. So we already discussed before. So I want to rephrase it. So the reiterated. The first one is completeness. So we need to make sure that our partitions covers the entire domain, right? Entire input domain. The second is disjointedness. Partitions must not overlap. Okay. So what are the steps to partition input space, right? And what are steps to use this approach to design test cases? Um, the first step is find the unit of functions to test, right? Can be functions, classes, or systems. Second is identify parameters of each unit. The parameters of each unit. This parameters define the input space. So these parameters can be the method parameters, or read from file, or user input, right? For example, find string is a string. This string is input, right? That is a parameter. Then we go to define the input space model. So which are our partitions actually. Um, so there are two general approaches to create input domain models, or the partitions. So one is interface based. We just look at the interface. We look at these parameters, and we define the partitions for the parameters. The second is functionality based, which is like a higher level, using a functional behavioral view of the program. For example, we look at requirements or use cases. Let's look at a simple example. Okay. In this example, so we have a class tree type, a triangle type. So it's a standard triangle classification. So we need to specify the three sides of the triangle. Okay. There's different types of triangles. The first type is a scaling, right? Scaling triangle, three unique sides. The three sides are different, have different length. Okay. The second type is isosceles, right? So it's two sides of equal length. Two sides are equal, but third sides are not equal. The third type is equilateral. All three sides are equal, right? And the other type is not a triangle at all. Using two different approaches, how can we do the partition, right? First, interface based for each input, right? For each input, three inputs, side one, side two, side three. For each input, we have a partition. Bigger than 0, smaller than 0, equals to 0, right? This is just an example, okay? Functionality based, we can define different types of triangles. First type is scaling, right? Like we have equilateral, we have invalid, we have different types of triangles. So we define these partitions using different approaches, right? Okay. This is a quick overview of what I already discussed before, right? So here, and then we will discuss how to measure the coverage of the input space. Okay. So this is the topic of our today's lecture. Okay. So how to test multiple inputs characteristics, right? And each input would have their own partitions. How can we do this test? So here we use a simple example. So we can consider 3 inputs with the following representative values from each partition. Here, 3 inputs. The first inputs, 2 partitions, right? The first representative of the representative value of the first partition is A, and the representative value of the second partition is B for the first input. And we have a second input, third input. Okay. Then we will discuss how we measure the coverage, the input space coverage. Okay. Actually, we have different approaches to do this measurement. The first approach is all combinations coverage, or ACOC, all combinations coverage, for these 3 inputs. So we want to cover all the combinations of these representative values. Okay. All combination coverage. So in order to design this test case, we need to consider all the combinations, right? For example, for the first input, we need to consider A, and we also need to consider A being combined with each of the values of the second input and the values of the third input. So we have this number of test cases. Actually, yeah, I have this number of test cases. It's here we have 12, right? Because the first input is 2 values, second input 3 values, third input 2 values, 2 times 3 times 2, right? It's 12. So we have 12 test cases in this case. Okay. So here is we consider all combinations of the inputs. Okay. Which is called all combination coverage. So as we see here, so we if we do all combination coverage, we need lots of test cases to cover a simple scenario, right? The second approach is also, this is what we actually discussed in our lecture for software testing, right? We use each choice coverage. So we only need to cover one representative value of one partition for each input, right? In this example, so we just need to cover each value once. Okay. So we can design a smaller set of test cases. For example, here, we can have only 3 test cases to cover the combination of 3 inputs using the each choice coverage approach. Actually, the minimum length of this test set is the length of the inputs, is the size of the inputs with the most representative values or most partitions. Okay. So here the second input has 3 partitions or 3 representative values. So the length of the test set is 3. Okay. Second way is a pairwise coverage. Third way is pairwise coverage. This is something between the all combinations and the each choice coverage. Okay. In a pairwise coverage scenario, so we need to consider the combinations of each pair of inputs. For each pair of inputs, we consider all combinations between them. Okay, this is pairwise coverage. And example here, for this example, right? We need to consider all the pairs. First pair, the first input and second input, right? We need to do A1, A2, A3, B1, B2, B3, right? And assign random values from a third input. For the pair of the second and third inputs, we do 1x, 1y, 2x, 2y, 3x, 3y, all the combinations of this pair, right? And assign any random value of from A, right? And we have how many? We have a 16 test cases here because we consider all such pairs, right? One, two, three, four. Yeah, we have a 16 here. Oh, no, not 16 test cases. It's just 16 test requirements because we have so many pairs. The first two pairs, the first two inputs, the pair, we have 2 times 3 requirements. First and first and third, we have 2 times 2 requirements, and the second and third, we have 3 times 2, right? In total, we have 16 requirements, but we only need 6 test cases to cover all of them, right? If you look at the 6 test cases, actually covers all the test requirements. Okay. Do we have any questions here? Okay. So here, so far we have treated all the partitions as equivalent, right? But in fact, people using the software is not in equivalent way. People use some inputs most frequently. There are maybe some dominant combinations of inputs, right? Here, so in this approach, in the next approach, we will pick one partition as the most important one and call it the base choice. Base choice can be the simplest choice, or smallest, or most likely, or the first choice. Okay, still the same example. So what is a base choice coverage? Choose a base choice partition for each characteristic or for each input, right? And we have a base test by combining the base choice from all inputs. Okay. And for each input C, so this test requirement contains the requirements for a test which vary the base test by using all other partitions for input C. So they might be hard to understand, but let's look at an example here. For this example, we choose a base choice for each input. We choose A for the first input, 1 for the second input, X for the third input as a base choice. So then we have a base test, which is A1X, right? And then we just vary, based on the base choice, base test, we vary each input at one time, right? So first time we vary from A to B for the first input. Second test case, we vary from 1 to 2 for the second input. We do this for all other choices of each input, right? Then here, so we see we have four choices other than base choice, 4 test cases other than base test. So in total, we have 5, right? So number of case tests is in this formula, okay? We have a base choice, base test, then we have other test, and each of them just is a variation of one input, okay? This is a base choice coverage. For this, for the example of the triangle type, we have so we could have this result. We have how many, each side length with 4 blocks, for example, right? 4 partitions, which means each side we have four partitions, right? So in total we have 10 test cases because base test plus for each side we have 3 additional choices, right? Is 1 plus 3 plus 3 plus 3 is 10 tests. Okay. And there's some discussions about the input space modeling. Okay, so like firstly is the all combination coverage, right? This is the most comprehensive one. So we need the most test cases for this coverage scenario, right? a test set that satisfies all combination coverage also satisfy others. Okay. Input space partitioning is hard to automate because it's very hard to automatically capture all the inputs. So it's hard to automatically test the input space coverage. Okay, to measure input space coverage. We can use coverage metrics of different approaches to measure the input space. We can do the calculation, but it's not automatic. So here I want to do an exercise based on the input space coverage. So in this exercise, so we have a program with 3 inputs, A and B and C. And we have the partitions for each input, right? And for each partition, we have just one representative value. For the input A, we have 2 representative values, A1, A2, or 2 partitions, we can consider this way. For verb B, we have 2 representative values or 2 partitions. For input C, we have 3 partitions or 3 representative values. So I want you to do the exercise for each of the following coverage criteria. Design a minimum set of test cases that satisfy the criteria. Okay. The first coverage criteria is all combination coverage. Second is each choice coverage. The third one is a pairwise coverage. The fourth one is a base choice coverage. So you can check the slides, go back, check the slides, and to see the definition of this different coverage scenario. And the slides are on Moodle, okay? And let's have some time to do this exercise, and let's have a break. And so after we come back, we will discuss the answers to this exercise, okay? I think the time now is, okay.